In section 3.2, we are now going to be reviewing how you can solve linear systems algebraically, both with the methods of substitution and elimination, okay? These two methods you should have seen in previous courses, so I'm going to go through them pretty quickly, okay? Let's start with substitution, all right? What I need you to understand is that substitution is a method most useful when at least one variable's coefficient in your system is equal to 1, okay? So let's run through a couple examples using this method, all right? Starting with the system that's over on the left-hand side, we have y equals 4x minus 9, and we have y equals negative 3x plus 5. Notice how both equations you have the y variables with coefficients of 1. That means this is perfect for substitution, okay? So what I'm going to do is take the expression of 4x minus 9 that y is equal to in the first system, and I'm going to substitute it in for y in the second system, because ultimately I'm trying to find when are their x and y values the same, right? So that's going to lead me to the equation 4x minus 9 is equal to negative 3x plus 5, which is now an equation in one variable that I can solve really easily. 7x is equal to 14, x is equal to 2. Now understand that's only the x coordinate of your solution. You need to find the corresponding y coordinate to go along with it, right? And I can do that by plugging 2 in for x in either of the equations, right? If this is going to be a solution to the system, I should get the same y value using x equals 2 in either equation. So I'm just going to plug it into the top equation, and that's going to end up giving me 8 minus 9, or negative 1 for y. So that means the solution to my system is the point 2, negative 1. And since I only got one answer from my substitution, I'm going to classify the system as consistent and independent. Okay. All right, let's go to the next example. Okay, so notice in the top equation, neither variable has a coefficient of 1 on it, but in the bottom equation, you do have both x and y with coefficients of 1. So this gives me some options, okay? What I'm going to do is I can solve the bottom equation for either x or y. It doesn't really matter. You have the choice. So I'm going to choose to solve it for x, which just is going to require me to subtract y over to the other side, okay? Once I solve it for x, I can take this expression that x equals and I can substitute it in up here for x, okay? That's going to lead me to 2 times the quantity of negative 12 minus y subtracted by 3y equal to 6. And now I solve that for y. I'll distribute. Okay, variables to combine together to give me negative 5y. Get my constants over to the other side. End up with y equaling negative 6. Okay. And then I'm going to plug negative 6 in for y into either of my equations in the system. I would actually choose to plug it in right here because I'm ultimately trying to solve for x, right? So I'm going to say that x is equal to negative 12 minus negative 6, which is going to result in negative 6. So that means the solution to this system is negative 6, negative 6. Only one answer, so just like the previous system, this is consistent and independent. All right. Okay, now let's move forward to the method of elimination. All right, so elimination is going to be most useful when all variables have coefficients not equal to 1 in your system. So if none of the variables have a coefficient of 1, elimination is probably your best choice. All right. Example over to the left-hand side here. We have two equations in the system, none of which have a variable or a coefficient on their variable of 1. Okay. So here's what I'm going to do. I'm going to take and try to make the coefficients of either the x variables or the y variables equivalent to one another. In this particular system, I think it would be easiest to make the coefficients of y equal to each other. So I can do that by taking the top equation and simply multiplying both sides by 4. Okay. That's going to give me an equivalent version of the equation just in a non-reduced form. So I'll rewrite that down here as 12x minus 8y equals -4. And then I'll copy down the second equation of the system. So notice the coefficients on y are 8 and -8 in each equation now. That's ideal now for elimination, okay? What I can do now is add the two equations together with each other. And what that's going to do is get the y variables to eliminate or cancel. And it will leave me with 7x equals 7. So I can now solve for x. X equals 1. Okay. Once I get my first value for my solution, my first coordinate, I plug that value into either one of the two original equations in the system to get my other variable's value. So I'm going to plug 1 in for x in the top equation of the system, original top equation. Solve for y. All right, so you can see my solution will be the 0.12, which is meaning this is another consistent and independent system. Okay. All right, next system. Once again, you can see none of the coefficients in either equation have are a 1 on any of the variables. So definitely want to use elimination here. I think it would be best if we got the variables or the coefficients on the x variables to be the same or be opposites of each other, okay? So I'm going to multiply the top equation on both sides by 6, and I'm going to multiply the bottom equation by 5. All right, so that's going to lead me to -30x plus 48y equals -576. And then the second equation would be 30x minus 45y is equal to 555. Okay. All right, now notice I have -30x and +30x. The only way those are going to eliminate is if I add these two equations together. Okay. Had both of those coefficients been of the same sign, let's say they were both +30x, then you would actually want to subtract your equations from one another. Okay. All right, now when I perform the addition here, x variables cancel or eliminate. 48y plus -45y would be 3y, and then -576 plus 555 would be -21, making y -7. Okay. Now I'll take -7, I will plug it in for y in either one of the two original equations. Once again, I'm just going to use the top equation. solve for x. All right, so one more time, solution is 8, -7, and we have a consistent and independent system once again. All right, you know the drill. Now it's your turn to practice. Pause the video, go to practice one, work through it yourself. You're going to have the option of using substitution or elimination. You get to pick, try to figure out which is the most efficient method to use. Use the method, solve, and once you're all done, come back to the video and check your work with mine.